Hey everyone, welcome back. So in this video, we shall be revisiting the moving average model. So we shall start with the moving average operator. Quite like the autoregressive operator, there's an MA operator as well. It's defined in this fashion using the backshift operator. So the definition of the moving average model of order Q is this, where W are the white noise terms. It can be reformulated using the moving average operator in this fashion. So the thetas are the parameters, they're the constants. And remember, we want theta q to not be 0, because if theta q is 0, then it is a moving average model of order q minus 1. Okay, so we want the last constant, theta q, to be non-zero. So there is an alternative way to write this. So many textbooks and maybe online articles, if you do read them, might define the moving average model slightly differently. So it might look like this, where instead of, so here I have plus theta 1, plus theta 2, and so on, they might have these negative signs in front of all the parameters. So let's recall the autocorrelation function of moving average 1. So this is the moving average 1 model. This is the autocovariance function. This is the autocorrelation function. So look at the form of the autocorrelation function, right? It's theta by 1 plus theta squared. So if theta is positive, the correlation is positive. If theta is negative, the correlation is negative. And quite similar to the autoregressive case, this will have implications for the smoothness of the time series, okay? So consider a series where theta is 0.9 and consider another one where theta is minus 0.9, right? So think about the correlation structures that these series imply and think which one will be the smoother one. So I've created a discussion question about this. Make sure that you go ahead and post your answers in the discussion forum. So next we move to the idea of non-uniqueness or uniqueness of a moving average model, right? So this is the autocorrelation function and this is the autocovariance function. So what do I mean by uniqueness or non-uniqueness of a model, okay? So is it possible to have two different moving average models, right? When I say two different moving average models, that means that their parameters, that is the thetas and the sigma, right? Sigma, which is the variance of the white noise, is different, right? So two different moving average models will have these different set of parameters. So is it possible that two different moving average models have the same autocorrelation and the autocovariance structure, right? So if you look at the correlation, if I substitute theta by 1 by theta, nothing changes. So calculate this, what this is with theta equal to 5 and with theta equal to 1 by 5, you'll see that you end up with the same number. So for the covariance part, calculate each of these numbers with sigma squared as 1 and theta as 5. And then recalculate these things with sigma squared as 25 and theta as 1 by 5, you'll see that you get the same numbers. So let's just look at this one. So theta is 5 and sigma squared is 1. This is 1. This is 5, right? Sigma squared is 25 and theta is 1 by 5. So 25 by 5 is 5. You get the same numbers, right? So even though, so this is a moving, both of these define different moving average models. However, they have the same covariance structures and same correlation structures. So this is the non-uniqueness of moving average, right? So moving average models are stationary. Covariance, correlation all depends only on the lag. So even though you have different parameters, you have the same covariance structures there. So it is hard to distinguish between these models, right? So if we look at a plot, of a moving average model, so say we generate an autocorrelation function plot from this model. However, the plot will look exactly the same whether it is this or this, right? So just by the plot, we cannot tell if the underlying moving average model has sigma square 1 and theta 5, or if it has, 20 variance is 25 and theta is 1 by 5. So from the plot, we cannot distinguish, or from the autocovariance or the autocorrelation structures, right, we cannot distinguish between these two models. We cannot tell whether it is this model or this model. So to get around this problem, we will choose only one of them, and to make this choice, right, which one of the two to choose from, we will use this the infinite representation that we did in the AR process. Okay, so let's see what is this infinite representation, right? Just a quick recap. So I'm just rewriting this this moving regressive moving average model, right? So I'm shifting, so I'm writing this as WT is minus theta times WT minus 1 plus XT. So then with this representation, we can rewrite WT minus 1 as minus theta times WT minus 2 plus XT minus 2, right? Rearrange the terms, and we can keep doing this infinitely many times. So this is the representation that we get. And if absolute value of theta is less than 1, this representation is valid. Like, remember, if theta is greater than 1, this kind of blows up, but if it's less than 1, this is a valid representation. And if a process has this representation, it's called as an invertible process. Okay, so between the two models, right, between the two candidate moving average models, we are going to keep the one that is invertible. So basically, given a choice, we will choose this sigma square is 25 and theta is 1 by 5. So let's calculate the autocorrelation function of moving average 2. We have done this calculation for MA1. Let's quickly run through this calculation for the order 2. So this is the model. Variance, right? So that's gamma 0. This is pretty straightforward. So lag 1, so that's covariance between xt minus 1. I've just plugged in the expressions for each of these functions. Remember, the surviving terms will be theta 1 wt minus 1 and this, and the other term will be theta 2 wt minus 2 and theta 1 wt minus 2. Basically, these terms will survive, or these will be non-zero. And basic properties of covariance, using those, you'll get this form. For gamma 2, that is lag 2, again the same strategy. You get this is the covariance for lag 2. So you can summarize all of that. So basically the correlation, right, for lag 1 is this. So that's the covariance divided by the variance. For lag 2, it is just this guy, and we know that for lags greater than 2, it is 0, right? So this is the autocorrelation function of moving average 2 model. Make sure you pause the video and you read this a little bit more carefully, and you're able to do these calculations fairly quickly and easily. So let's generalize this. Let's look at the autocorrelation function of an MAQ model, right? So this is an MAQ model. So variance calculation is easy. Variance of xt is variance of this, and we know that WTs have variance sigma square, that is here. So basic properties of variance will give you this. Lag 1. So for lag 1, again, I have substituted expression for xt and xt minus 1. You need to be a little bit careful about writing the expression for xt minus 1, right? So xt minus 1, so all of these t's get replaced with t minus 1. So wt minus 1, wt minus 1, that's minus 2, t minus 3, and so on, and the last term will be t minus 1 minus q, or t minus q minus 1. Okay, so be careful when you write down these subscripts, but there is a pattern here, and just follow the pattern. So again, we have to pull out all of these common terms, right? So I have WT. There is no WT here. There's WT minus 1 here and WT minus 1 here, so this will survive. So the next term here will be theta 2 WT minus 2, and this theta 1 WT minus 2, so that will be the next term, and so on and so forth. So you can get a pattern from here, and be careful to write the last term correctly, right? So here you're going to go back all the way till theta Q WT minus Q, and then you'll have this term from this other side. Okay, so just pause the video and carefully write down these expressions. And then again, basic covariance properties, you get this. So once you can write the second step, this is not too hard to write. So this is for lag 1. In general, for lag k, right, you can, again, so the covariance is, so this is the term for xt, and this is the term for xt minus k now. So for xt minus 1, we had wt minus term starting from wt minus 1, and here we'll have term starting from t minus k, right? So you go here and you substitute, instead of t, you'll have t minus k. That's the only difference. Again, you pick out pairs that have common terms in them, right? And make sure you write these coefficients correctly, and this is what you get, right? So this is the autocovariance function, and of course for lags greater than if the lag is greater than q, right, then this autocovariance is 0, because there will be no terms in common, right, between xt and xt minus k if k is greater than q. So you can summarize this, right? The autocorrelation function is the covariance divided by this variance, and there's a pattern here, right? So rho k, you start from k, theta 1 k plus 1, theta 2 k plus 2, and so on, theta q, and you have this q minus k. So this can be a little bit confusing, right? So I have tried to provide you with some outline of how to think about this. It is important that you think about this on your own and write these terms on your own without looking at this video or without looking at the slides. Okay, think about this. So this is the autocorrelation function of a moving average MEQ model. Of course, for k greater than q, it is 0. I have not written that here. So that's all in this video. With now that we have a slightly better handle on the autoregressive and moving average models, we shall move to the ARMA models, which is basically an autoregressive moving average model. See ya.